It's a restoration of a historical landmark, and that's why the bridge was not replaced in its entirety. But only 8 major pieces of the bridge remain, and I'll talk about those as we go along. The original bridge was built by the Lackawanna Steel Company. It had a wooden deck. Lackawanna Steel Company is from Buffalo, New York, and all the steel was made in Buffalo. Some of the original stampings are on the original beams. Originally, it had a wooden deck. It was hand operated and spent more time in the up position than the down position because of traffic on the canal. So many people who would cross the bridge crossed by foot. But of course, that changed over time. Now, these are the topics I'm going to discuss on your left. The contractors, the pits, the iron workers, working in the snow and rain, the installation of the beams, painting the bridge, weighing the bridge, and how the bridge works. Many of the things that went on I'm not going to talk about. The removal of the old counterweights was underground, happened before I had a chance to take any pictures, and of course I couldn't take pictures of what they were doing. The concrete work, installing the cables, the electrical work, and renovating the control tower. Ted Elbers was the project superintendent. He was from Buffalo area. He worked for Whole Industries, which managed this project. He was there every day of the 22 months, except for a couple of doctor's appointments. Kevin Canan was the state engineer in charge. He had somebody working for him who was there quite often. He would come, every few weeks for important issues. These are the skills that built the bridge. Construction laborers, concrete masons, machine operators, iron workers, carpenters, electricians, millwrights, painters, and inspectors. And there were many inspectors from different companies. These were the main contractors. Whole Industries was in charge of this project, and all of the other contractors are subcontract to them, except for the parts that were made in, the mechanical parts made in the United States, which were contracted, I think, to New York State. I'm not sure how that worked. But the painting, there were several engineering companies, but Erdman Associates provided the engineer who was on site daily. Okay, work on the bridge really began in 2017 when the state of New York contracted with Bergman Engineering to redesign the bridge, to design the process of renovating the bridge. That's what they did. The reason why the bridge was going to be replaced is because of corrosion. So there's corrosion on the bridge everywhere. Many elements of the bridge showed a lot of corrosion. These are just some pieces, angle irons. This is a main beam. So there are 11 main beams, and there were holes in the main beams that were 5 inches in diameter. This piece of shale came from a main beam. If I would like to pass it around, if you're afraid to touch it because of, I don't think that you're going to get COVID from that. So I wouldn't be fearful of touching it. Now we were driving, 40,000-pound trucks were being driven over that bridge. And that was really gutsy because I don't know if it was ever really designed for that weight. But when it was rebuilt, it was beefed up a great deal. Work started on the site on September 4th, 2019, and the expectation at that time was it was going to be a 15-month schedule. to be finished in November of 2020, is that right? But actually, it ended up being a 22-month schedule, and I'll tell you why it slipped 7 months. Okay, this is a diagram of the bridge. The bridge itself is 139 feet long and 64 feet wide, including the walkways. But for the traffic pattern, it's only about 50 feet wide. When you look at the bridge, you only see half of it. The other half is under the ground. And those are the two pits on each side. Those pits are 35 feet deep. They go at least 15 to 20 feet below the bottom of the canal. And one of the big problems that nobody ever anticipated was the canal was leaking into the north pit. And no one knew that. So when they started the bridge, one of the first things they had to do was repair the north pit to stop the leaking. That's just one of many unforeseen problems. Let me think about anything else I want to do. I'm going to go in the pits in more detail because that's such an important part of the bridge. The bridge is a bowstring truss bridge, and it's called a table bridge. So most table bridges have the counterweights outside. It's much easier to construct them outside, but this one has them under the ground. And today, you wouldn't build a bridge like this. You wouldn't build a bridge with counterweights. You'd support the bridge with hydraulic pistons on each corner. There are 16 lift bridges on the canal. Whole Industries contracted to rebuild 2 bridges for $16.5 million. That was the contract to the state. I do not know how much it overran, but they lost a lot of money on this bridge. And one of the reasons, there's 2 reasons, but one of the reasons was that they didn't really anticipate the problems they were going to get into. Now, the very first thing they did was they had to remove the counterweights. And in order to do that, they had to raise the bridge to the up position, which is what it's in here. It's in the up position. And they, on each corner of the bridge, they supported it with columns, which you see here. This is taken from in the pit. So the counterweights are gone, but I'm really just talking to you about how they supported it for the 22 months. Wow. Now, this is one of the 8 members that was not replaced. So the 4 legs of the bridge were not replaced. The bowstring trusses were rebuilt but not replaced. And these 2 beams underneath, there's 2 beams underneath that support the legs, 2 legs on each side. Those were not replaced. In order to stabilize the bridge, also they strengthened the bridge by putting a tie all the way across the arches. They did not want the arches to move throughout the process. So they strung steel rods all the way across the 139 feet of the bridge with a clamp on each end. And this shows the rods and the clamps, and they were there until the main beams were replaced, and then they were removed. Like I said before, there's 11 main beams. The third thing they did to stabilize the bridge is they had a removable beam underneath that they moved as they removed main beams. So they would move this along as they would take a beam out and put a beam in. So they replaced almost all of this bridge, but if you walked up to the bridge and you looked at it, you'd say, well, there it is, it looks pretty normal. But it wasn't normal. They were doing it piece by piece, 1 piece at a time. Now I'm going to talk about the pit chambers, which are 35 feet deep. They contain the counterweight and the 3 shivs that are used to make the bridge go up and down. So those are very important pieces, those shivs, and they're basically pulley wheels, but they're big, and we'll talk about that as we go along. Let's see. I don't know if there's anything else I want to tell you from this slide. Just to say this, that the bridge is driven up by a motor which drives rack and pinion, and there are 4 cables on each side of the bridge. So S6 is connected to one that goes to the other end of the bridge. So the total length of these cables never changes, and they're always under tension in order to make the bridge go up and down. But I'll talk about that a little bit more a little later. This is looking down in the pit, the 35 feet from street level. After the original counterweights were removed, this is a view of the pit. And here we see one of the legs of the bridge, that beam I told you about. And here's those columns that are supporting it, part of the 3 things they did to stabilize the bridge. But this is a view of the pit after the original counterweights were removed. So once they did this, they had to rebuild the counterweights. So this is, the carpenters had to go in there in a very narrow area and build these forms. These forms are 10 feet high, 48 feet long, and 4.5 feet wide. And they're going to fill that with concrete. And that's going to be the first part of 3 parts of the counterweight. I'll show you the other parts as we go along. Oops, one more thing about this. You'll see these, on each side there are these supports, and on those supports they're going to put the new internal beam that goes into the concrete, which really holds the concrete counterweight together. This is what, when they raise the counterweight, it's actually directly connected to this double steel beam. Here is the beam now inside the forms with rebar around it, and these black things are these cable attachment bolts. So that's what they're going to attach the cables to raise and lower the beam. Here the bolts are here. And here they're pouring concrete now into that form to make the first part of the counterweight. Here's the counterweight now after the concrete has been poured. And you can see rebar on top of the counterweight now to build the second part. So there'll be 3 parts. These are 2 chambers that more weights are going to be added to. I'm just showing the bolts that'll hold the cables to move the counterweight up and down. Now, the third part is steel plates. Now, steel weighs a lot more than concrete. It's 6 times I don't remember the number, density of concrete, but they'll add quite a bit of steel in these chambers that they're building. There's 2 chambers, but I can only see one here. So they're adding the steel, then they're going to build a form around that and create a wall around that form and fill it with concrete. So you'll have these 2 cribs. And they're preparing here blocks to add and subtract these blocks to bring the counterweight to its final weight. They'll weigh the counterweight and the bridge 3 times in order to make sure it weighs what they want. So a lot of work goes into balancing the bridge and the counterweight. Here, now you see the forms are all taken out now. The counterweight, this is the upper part of the counterweight, these 2 cribs they built to accept these added blocks. So they're always working with these blocks to get the weight right. They have to weigh the counterweights just like they have to weigh the bridge. So there is this steel rod in here, and I don't see it here. They build this contraption on top to lift up the counterweight. The counterweight is sitting on railroad ties on the ground right now in the pit. And they use this steel bar, which is about 2.5 inches wide and 6 inches deep. Solid steel that goes all the way down to the counterweight. So here's that bar hooked to the counterweight, and they put a load cell on this contraption they built on the surface, and they're going to lift the counterweight up. So they raise the counterweight 1 inch. This is on the down position, the up position, and from this, the pressure, the hydraulic pressure on this, they can tell the weight of the counterweight.
Not the weight of this.
The counterweights are approximately 400,000 pounds each. The bridge is 800,000 pounds, plus or minus a couple thousand. Yes.
Those counterweights are perpendicular to the road?
Yes, they go across the road.
Okay.
Right. You can ask me questions and go on. Yes.
Just wanted to point out that it looked like all of your steel in the pit was hot dip galvanized steel.
All the steel they put on was galvanized except for the shivs, and I'll talk about those. Okay, I'm just going to say the things, iron workers were there for most of this project. Just to mention some of the things they do. Here's some of the strengthening of the bowstring truss. There's much of that went on. Here they're drilling gussets, drilling and aligning a gusset and the bridge itself. They do a lot of aligning of holes for bolts. Okay? The number of bolts in this bridge has got to be in the hundreds of thousands. Aligning plates and sidewalk. This is aligning the sidewalk beam. This is a sidewalk beam being aligned to the receiving point. So that they did a lot of this sort of work. The iron workers also built a barge, which they put in the canal. It was a floatable. These 3 floating elements built the barge out of it. Here you see them, and this stayed in the canal for over a year. Even when the water level in the canal was dropped, it was still there. And the electricians and the iron workers used this all the time for probably about 18 months, I would guess. Now the main beams, this is about replacing the main beam. It's one of the things the iron workers did. So here's one of the main beams. It's the N1. And the first thing they do is, with an acetylene torch, they cut the beam a certain way so it'll easily swing away from the bridge. Here you see him cutting the beam. Now, I think it takes a lot of skill to use one of these torches and not cut off your leg. Oops, what did I do? Okay, so here you can see the beam is being swung away from the bridge, and you can see how corroded it is, being lifted away. And usually they only stay there about 2 days before they remove whatever they're removing. They have trucks to remove them. They also remove the plate that hooks the beam to the truss. Yes?
So this beam that they're removing runs across the road.
All the main beams run across the road.
So and it looks as if this might be the south side end.
That beam was the north side.
North side, okay.
Okay? So these have to be removed as well. And here's one of those plates that attaches the beam that's been removed. Now they're going to install a new beam. Now, all the new beams are wider and heavier than the old beams, and the road beams are much wider and heavier than the original road beams. So the whole thing was built much stronger than original. This is a new beam being lifted into place. Now, the bridge varies in width. It's narrowest in the middle and widest on the ends. That's because of the way they strengthen the bridge. They added metal plates to rebuilt the entire lower portion of the truss, adding metal plates to make the truss much stronger. All the beams were made to the same length, but the bridge is a different length along the bridge, so they have to be fitted by trial and error to be placed in the bridge. So here the beam is coming into position, to be positioned, to be brought into position. Now here they're drilling a plate to fit the beam in the location they're dealing with. And they would drill a number of these plates. They had plate material in different thicknesses. So they would estimate what they needed, and if they needed to drill a different plate, they did that. Here's one of the plates being hoisted into position to fit the beam. And he's installing that plate. I'll show you this. This is the plate. Now this is all new material. And this is all new. That's the lower part of the truss. And now he's taking angle irons and screwing the beam with angle irons to the plate. And that's what's going on here. Here he's aligning the plate. And I don't know if everyone, but there's 11 beams along the length of the bridge, and they are different thicknesses to compensate for the change in thickness of the support, these things, the change in thickness of the lower part of the truss. So this is all the installation of the beam. And that's the finished beam installed. So this is the same location where I showed you the beam was removed. They could install a beam like this in about 4 hours. Night shifts. Okay, during the day, the highest number of people I counted working on the bridge was 25 at one time, and at night it ran about 6 to 8 normally. But there were times when there were only 2 to 3 working at night. But they worked most of the time 2 shifts, 10-hour days. So these are night shift pictures. It's another night shift picture. And one night shift that I was there, they were installing the sidewalk support. So that's what's going on here. These are the sidewalk supports. And you see it being trucked in. The crane is there. And the iron workers are there attaching it to the bridge. So, you know, the hope was they'd install all of them on one side in one night. These are the new road beams. There are 96 road beams. They installed all 96 of these in 2 days. But they didn't tighten the bolts. The bolts were installed loose. So they tightened all the bolts later after they had installed the road beams. So they would carry 2 road beams in on one load from the crane. And, you know, the iron workers would put them together. It's like a super erector set. And these pictures are really just installing these are the road beams. Now, this is a picture of the bridge with the main beams, the road beams, and the sidewalk supports installed. That was September 16th, 2020.
So where did you take this picture from?
I took a lot of pictures from the roof of the Bax factory. They gave me permission to do that. So I'm only going to show you a couple of those, but that's where I took a fair number of photographs from there. Now, you can go and see a lot of this at the canal. If you go to the Bax factory, to the area where the bridge meets the road, and you can look up, you can see the entire understructure where you can see the main beams, the lateral supports, the gussets that hook all that together, and the road beams. So you can see that picture very easily. Bolts. So here's one of the bolts. You can pass it around. They were all galvanized. They used bolts because they were stronger than rivets. Bolts, the iron workers would tighten the bolt, and after the bolt was tight, they would turn the bolt 1/3 of a turn more. They did that on every single bolt. Bolts were inspected. This guy is spending his day inspecting the bolts, and what he's looking at mostly is not the tightness of the bolt. What he's looking at is how many threads stick out from the bolt. There's a specification of only 2 or 3 threads can stick out. So if the bolt is too long, it has to be replaced with a shorter bolt, and vice versa. So that's all has to do with corrosion requirements. How much the threads stick out of the bolt. Working in rain, there was never rain they didn't work in. Here you can see an iron worker tied off, so they were very important. Safety was very important, so you had to be tied off if you worked on the bridge. They would erect a tent if they needed to keep their work dry on a rainy day. They worked in snow all the time. A lot of concrete was poured with snow on the ground. This is snow. These are millwrights working when it's snowing pretty hard. These were electricians working in the snow. Notice on very tall ladders. Now, when they poured concrete during the winter, they used heating, saline heating conduit to keep the concrete warm. Concrete had to be kept at 50 degrees Fahrenheit for a week. So they would lay the sandwich. They would lay these a layer of canvas, then these conduits, and then on top of the conduits they would have another layer of canvas, and it would sit like this for a week, and there would be run by a furnace. So portable furnaces were being used all the time for heating if they needed heating. This is a portable furnace here to supply heat for concrete. And these are tarps where they could build something to keep the heat in if they needed it. They poured some concrete on the edge of the bridge, and these were keeping the concrete warm. The pits were open through the winter, but they built these plastic chambers that would keep snow and rain out of the pits, and also that would allow them to heat the pit if they needed it. So this is the inside of the pit with those portable covers. When they needed to work and the portable covers were in the way, they would remove them. And here they're pouring concrete, and covers are all removed, and then when they're done, they'll put them back. You'll see this tube here, that's from a furnace that will heat the pit because there's concrete being poured. It's got to be above 50 degrees, so that's what they're doing. Here's another one here. Okay, after the main beams and the road beams were installed, then they wanted to install the walkway stringers. So that's these things sit on the walkway supports. These are the stringers that will hold the grate for you to walk on. And here's a picture of the bridge with the walkway stringers in place. Now they're going to install the road gratings. So the road gratings on this bridge are very different from the road gratings of the original bridge. They're single, all welded, galvanized pieces, and on the edge they're 4 to 5 inches thick with supports running through them. I will show you what the old grates look like. These were like puzzle pieces. They could probably install them all in 2 days, I don't know, very quickly. But a lot of them were not bolted down. because they didn't have the mechanism to drive the bridge up and down. They needed to install them for safety reasons, but then they would remove them when they needed to do installation of equipment that drove the bridge up and down. So that equipment was all really late. We'll get into that. Here you see a road grate being installed. These are just pictures of the iron workers doing this. So some of them were bolted down and others were not. They're not welded down, they're bolted down. This is what it looked like with the road grates installed. And you can see these are loose still. Now these are the walkway grates. Now these things are only about an inch thick. And that's what the old road grates look like. And they were welded. And a lot of the old welds were broken on the old road bridge. So if you sat by the bridge near it and you watched traffic go over, it would be so loud you couldn't hear yourself talk. Yeah. But if you go to the new bridge, it's really, really well constructed. So they're installing the sidewalk grates right here. These are now see the thickness, it's very thin. It's the same thickness as the old road grates. Whoops, what did I miss? Okay, the original railings were removed. They were refurbished, painted, and then put back. There was a complaint made they put them back wrong, and they proved that they put them back exactly the way they came off because they had photographs of. So some residents raised this is a contentious issue, but the sidewalk rails are being installed here. So now we have the bridge with the road grates, the sidewalk grates, and the handrails installed. The next important thing is they're going to paint the bridge. They're going to paint the main members of the bridge. This took 6 weeks. They covered the trusses completely. They were going to paint the trusses with these canvas structures, which they can control the atmosphere in there. They used furnaces to heat them. See, what am I doing here? Now, this is the train of 4 main pieces of equipment that were used for painting. There is in here a sandblasting unit, a compressor unit, and a painting unit, and I don't know what else. I don't know what the 4th one is. There might have been a unit to remove sandblast debris. I'm not sure. That's what this is, for removing particles. But this sat there for a long time. It was very noisy. If you walked uptown to the library or any place, you could have heard this from a long distance because it was noisy. That's what it looked like with all of the canvases in place for both sides. This is from my photograph from the canal level. This is inside the painting canopy. So this is one of the painters did this. I asked permission to go photograph it, but they wouldn't let me.
So was the original paint lead?
I don't know. And I
When
don't know.
they sandblasted it, whether that 4th one was to protect the...
They sandblasted it all off, whatever was originally there. Then they added 4 coats of paint. In this photograph, you can see 2 of the coats. You see the red, the white coat and the red coat. But I don't know the composition of the paint. I'm sure it's it'll stand up, whatever it's supposed to be. You'll see paint cans. A lot of painting was done by hand, and when the main job was done, the arches, they came back and did a lot of other stuff, a lot of touch-up, a lot of other things that they painted as well. I want to tell you about the millwrights. I talked about the iron workers. So the millwrights were involved for the almost full 22 months of the project. And what the millwrights do is they install precision equipment that takes fine measurements. So here you see them using some kind of an instrument. I'm not sure what that is. they installed and aligned a lot of things. This is a theodolite. It's an instrument for measuring several angles at the same time, vertical and horizontal. So they had portable ones, but they also had them where they placed them somewhere on the bridge for something they were doing. And here they are aligning this shaft, and that's the main drive shaft. So we have 3 shafts in the bridge that go across the bridge. 2 balance shafts, one at each end, that balance the counterweight and bridge, and the drive shaft. Now, it took them, I will show you some parts of the drive shaft, but it took them 3 weeks to align the drive shaft. It weighs 8,000 pounds. When the shaft was aligned, you could turn that shaft with hand pressure. So that's amazing to me. Another thing that the millwrights did is they managed how the bridge rests. They have to align the bearing plates so that when the bridge sits on the concrete, every corner of the bridge sits flat. So I'm going to show you that. This is a load-bearing plate that goes under the foot of the bridge. Here's where it goes. This is the load-bearing plate and its shoe. And there are 4 of these on the bridge, 1 on each corner. So you can easily see these when the bridge goes up if you go by the library. You know, they're very visible. When the bridge comes down, this shoe meets this resting point. It's called the live strike plate. So there are 4 of these, 1 in each corner, and when the millwrights would adjust these things, their angle in 2 dimensions and their horizontal position, so that every time the bridge came down, it rests perfectly flat on those things. Weighing the bridge. So I mentioned the bridge was weighed 3 times, similar to weighing the counterweights. They built a column on each corner. They installed a load cell and a piston to move the bridge up. They would measure the weight from the load. They would lift the bridge up, and they would measure the weight by a load cell, these load cells. So they had 4 load cells. So these were very precise. And on the final weighing, the bridge weighed 799,230 pounds. Now, okay, so.
With the snow?
Huh? With the snow. There is a specification. We'll talk about that in a few minutes. I'm going to talk now about the parts of the bridge that make it go up and down and some of the specifications that have to do with those. This may be, I hope this isn't confusing to people. Okay, so we have road level here, and the bridge in the down position is shown. In order to make the bridge go up, we need to pull this cable, S6, in this direction. If we do that, that forces the bridge to go up. S6 looks like it gets shorter, but that's taken up by S8 over here on the other side. And when we want the bridge to go down, we have to pull S5. Now, the bridge weighs, the specification was that the bridge weighed 4,000 pounds more than the counterweight. 1,000 pounds on each leg. So that's why we have those 100-pound blocks that were moved around, so we could get 1,000 pounds of additional weight on each leg. So you would think that when we raise the bridge up, if we just let it go, it would just fall down because it weighs 4,000 pounds more than the counterweight. But actually, there's 7,000 pounds of friction in the system to move all the shivs and cables. So in order to get the bridge to go up, we need to apply 11,000 pounds of force, and to get it to go down, we need to apply 3,000 pounds of force. So you need to apply force each way. And there's, you don't need to know all these numbers, but the important things is, so there are three shivs on each side of the bridge. The balance shiv here and the upper and lower shivs. We'll talk about those. So the balance shiv and trunnion, that's this thing. Now they're installing the balance shaft. This is the balance shaft. It goes in two parts. This is inside the pit. I'm inside the pit, and that's the balance shaft across the inside of the pit. This is all temporary stuff in here. Oops. One back. Okay, so that's the balance shiv. That's the pulley. That's made out of drop forged steel. It is not galvanized. So the state of New York was responsible for these shivs. They were made 3 times. The first time they were welded, and they failed state specifications. So the state wanted them made again, and the welded ones were repaired, and they also failed state specs. So then the state said, well, we want them made out of drop forged steel. So this is a single piece of steel that's been machined. It's 5.5 feet in diameter. It was a solid chunk of steel before they started this. So all the shivs are solid drop forged steel. So here you see the piece with its shaft. The shaft is welded in, and there it sits in its trunnion. This is the heaviest piece loaded into the bridge. It was 28,600 pounds. And there are 4 of them. So that's the finished shiv, and 6 cables go on that shiv that balance the bridge and the counterweight. The bridge is always in balance with the counterweight, except for a small delta, which I mentioned, a few thousand pounds. So here they're installing that main shiv and balance shiv and with its trunnions. Here you see it being lined up with the shaft. And here it is in the pit. Now here's the balance. Here's the balance shaft, and here's the shiv. The shiv on each side. Here's where it's being attached. The cables now are being attached to the counterweight, and then the cables are attached on the other end to the bridge on this long beam that goes across in the pit. I mentioned that before. That's an original beam. These are original legs. Now the upper and lower deflection shivs are what ties everything together to go up and down. These shivs, so did I do this right? This is the upper deflection shiv. It takes 2 cables, the S4 and the S5 and S6 I showed you in the previous slide. Here it is in place. So now every time you drive up to the bridge and you see the bridge go up and down, you're going to see that shiv. And you're going to see those cables move. Those are the cables that are moving the bridge up and down. One cable is needed to pull it up. The other cable is needed to pull it down. So that's the upper shiv. This is the lower shiv. And he's installing the lower shiv here, moving it into position. Here you see it, and this is a much later picture, but here you see it from the pit. Attached to the counterweight. It's attached to the beam, not the counterweight. This is a picture of that lower shiv facing the upper shiv. So those are the two cables that you see. This cable anchors to the floor. This one goes to the rack and pinion.
And each one is 28,000 pounds.
No, just the 4 balance shivs. Those shivs I just showed you were much smaller. Okay, so going back with respect to your question, oh, I'm sorry I did this. So these are the small shivs. You know, they probably only weigh 1,000 pounds a piece. I don't know what they weigh. This is the one over here that weighs 28,000 pounds. Now, those are the original lower shivs, deflection shivs. They were cast iron, and they're now in the park, and you can see them, you can put your hands on them, the whole deal. But they're cast iron, they're not like what we have today. Now, I want to show you the drive shaft and rack and pinion that's used to drive the bridge. This is the main drive shaft. I told you that it took them 3 weeks to align this. They took them 2 weeks to align each one of the balance shivs. So aligning the 3 shivs was 7 weeks of time. It's a long time. This is the main drive shaft. If you walk on the walkway and you look down through the holes, you can see this. You can see this shaft. You can see it very well from near the box factory. So this is the main drive shaft, and it's driven on each side by a rack and pinion, which is driven by a motor through a gear system. So this is the motor, 20 horsepower motor. Now, I told you that we only have to move 3 to 11,000 pounds, but the state specifications were that if you had a lot of snow or you had something on the bridge, you had to be able to move an additional 40,000 pounds up and down. So when this was all tested out, they loaded an additional 40,000 pounds on the bridge and made sure that it worked right, which it did. So this is the motor. Here's the drive motor in position. You can easily see this from the box factory, from the canal level at the box factory. The motor drives gear reducer, which drives the rack and pinion, which is over here. This is the main drive shaft. This is the rack and pinion, so it's a pretty standard item, but that's the picture of it. Here's again the rack and pinion, which drives it. Now, you can see this view from the library. Near the canal, you can see the rack and pinion. You can see where it attaches to the, well, here's the rack and the pinion is over here. You can see this, and you can see the cables that are going to move the bridge one direction or the other. We also have a brake on the bridge in case it moves, I guess. So it has an electrical brake that can hold it up or down. So on June 11th, 2021, the bridge moved 3 feet for the first time. They drove it up, a motor wasn't connected. They drove it up with an electric drill. A 2 horsepower electric drill. So here's its first movement since September of 2019. And this is opening day. Now, this is opening day, July 2nd, 2021. One more thing I want to say. The bridge was 7 months over in time. 3 to 4 of those months were because of the shivs, the 12 shivs. They had to be reworked 3 times. COVID might have played a role in the shivs, but I don't think there was some COVID problems on the bridge, but I don't think it delayed the schedule. The remaining scheduled delay has all to do with unforeseen parts, unforeseen problems. So even if the shifts would have been on time, I think it would have been between 3 and 4 months longer than they anticipated. I think this is the opening day, and they installed 800 lights on the bridge. This was Fairport and the Canal Authority wanted this, so they did it. Those lights can change color. They'll probably be on display for the holidays. It's worth going to look at. Thank you. Yes, now for questions.
How long ago was the last rebuild?
1988, there was a major refurbishing, but it was never rebuilt. The biggest thing they did was converted it from a crank bridge, a hand crank, to put an electric motor on it. But that was a long time ago. I don't know the history.
Now, Dan,
Yes.
you
Yes.
said you took most of these pictures yourself.
Yes, most of these I took, but all the pictures taken from in the work area were taken by people who were working there. I put their names down. I got a number of them from the project superintendent.
And the terminology, I mean,
I learned a lot of it along the way. Yes.
I have a tidbit which is not building of the bridge, but that is you started the show with that plaque that's on the post there.
Yeah.
There's a story that goes with that. Does everybody here know Roger Maciel? I've known Roger for decades. He's cut my hair a lot. And I was trying to he knew I was with the Canal Society and ran a canal website. And he told me the story that the guy that was supposed to paint the bridge quite a long time ago got sick and tired of taking those plates off the bridge to paint and then have them put them back on again. And he said to Roger, I'm gonna throw them in the canal. And Roger said, don't do that, give them to me. And the guy did. And Roger had them in his basement for years. And one day he said, I really should do something with them. So he gave them to the village.
Oh.
The village lost them temporarily. And they were finally found and sent to the Canal Corporation. They sort of disappeared again with the Canal Corporation. I knew the head of the Canal Corporation at the time, and I wrote to her and said, where did these darn plates go? And they found them again, and they sent them to the Pittsburgh office over here. The guy over there called me and says, I got them, I'll put the one back. That's the one you showed. The other one wouldn't fit anymore, because originally West Street went down there and it was truncated. And when they got rid of the West Street and they continued the arch, there was no place to put it. So, it's upstairs now.
Okay. That's a good story. I didn't know about that. I didn't know you could take any of it apart because they were all put on with rivets.
Rivets, yeah.
Yeah, I mean, you know, with bolts.
How many plates were there?
Plates.
One on the northeast corner, which is still there, and the one on the southwest corner. You just paint over them. Good question. That's fine.
Yes.
I was wondering if there was any other bridge there prior to this? Or was this built at the same time?
No, there was a bridge there prior to this. If you look at Historical Society photographs, there was some kind of a wooden bridge that spanned the canal in that area.
Smaller than.
Yeah, the canal was not nearly as wide.
I don't think so, no. And I don't think they used the height either.
Had to widen the canal at this point, 40 feet
Yeah.
or so.
Now, this, yes,
I have a few pictures of the reconstruction when the canal was wide on my website, eriecanal.org. So you can see some pictures, what it used to look like.
okay. Any other questions? I thank you for your attention.